Photosynthesis can be divided into two processes, a light reaction and the Calvin cycle. During the light reaction, solar energy is converted to chemical energy via the reduction of NADP to NADPH and ATP synthesis. This occurs in photosystems 1 and 2 embedded in the thylakoid membrane of the chloroplast. The structure of the photosystems is composed of reaction center complex and light harvesting complexes. The conversion of energy involves the splitting of water and linear electron flow, which results in releasing oxygen, forming NADPH and producing ATP. Moving on to the focus of this video, which is nickel iron selenium hydrogenase, we can see there is a nickel ion centered within the quaternary structure of the enzyme. This is found to be an active redox center of which the oxidation states alter between 1, 2 and 3, which allows for the transfer of electrons for hydrogen generation. An attached selenocysteine residue within this specific isoform replaces the first cysteine residue of the C-terminal commonly found within the greater hydrogenase family. The result of this seemingly increases the enzyme's tolerance towards oxygen. There are 3 clusters of 4 iron, 4 selenium groups found within the small subunit of the enzyme's complex, which are found to supply energy to the active nickel site for hydrogen splitting by means of an electron transport chain provided by iron's capability of altering oxidation states. The reaction of nickel iron selenium hydrogenase is H2 converted to 2 hydrogen ions, 2 electrons, of which produces 260 units per milligram of hydrogen gas. The kinetics of hydrogen production via nickel iron selenium hydrogenase is quantified at a km of 12 micromoles and kcat per km of 8.58 times 10 to the power of 7 per mole per second. The optimum pH for enzymatic function has been observed at a pH of 6 and a maximum efficiency is reached at a temperature of 85 degrees C. The half-life of nickel iron selenium hydrogenase has been measured at 75 hours at a temperature of 80 degrees C and therefore is viable for many hours when being utilised for hydrogen gas production. Now moving on to the applications. The ability of nickel iron selenium hydrogenase to generate hydrogen from the splitting of water molecules can be used in synthetic photosystems to produce a renewable source of energy. An anode in photosystem 2 is linked to another anode made of titanium dioxide containing a synthetic dye whose role is to replace photosystem 1. Reversible cycling of electrons and protons is carried out between the photoanode complex and the nickel iron selenium hydrogenase used as a cathode. The result of the flow of particles is pure hydrogen being produced. The idea of lying in the anode composition is mimicking the mechanism of photosynthesis present within cyanobacteria. The composition allows there to be absorption of red, blue and green light. However, currently there are some issues about using this system in reality, so more research is needed in order to reduce potential errors on large-scale production. The selenocysteine group found in the protein molecule needs deeper examination so the kinetics can be altered to increase production. There are also costing implications to consider, as the metals required in redox reactions are expensive. Finally, there is the problem of storing pure hydrogen due to its volumetric density, which will need to be overcome. Now we are looking at the potential of using this enzyme to produce hydrogen fuel in more detail. In recent years, there has been an increasing amount of research into reusing renewable energy as a fuel source, with one of these sources being hydrogen fuel. Hydrogen is a great option to be used as a fuel source as it is light, abundant and has a great energy efficiency. In order to have a supply of pure hydrogen, molecules which contain hydrogen, such as water, need to be split. This process can be carried out using nickel iron selenium hydrogenase in electrolysis when it is incorporated into a semi-artificial photosynthetic system. The pure hydrogen is stored at a high pressure, being mixed with oxygen in a fuel cell. This reaction causes electrons to flow, which creates a current that can be used as a fuel source. By using hydrogen fuel, there are no harmful waste products produced, as there is when using more traditional fueling methods, which means that it's better for the environment as well as being renewable. Currently, this technology is still in the early stage of development, but research into fine-tuning this technology for future use on a large scale is well underway, with no doubt that nickel iron selenium hydrogenase will be a key part of this development for the future.